This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's problem is to compute the integral from 0 to pi on 4 of 30x squared plus 30 sine squared x divided by x squared cos squared x plus cos squared x dx. The constant 30 can come out the front, so we will ignore it some of the time for convenience. The textbook approach for solving this integral is first to apply a partial fraction expansion, and then we apply appropriate substitutions. After presenting this, we explain why it works. The need for a partial fraction expansion comes from the fact that we have a mixture of trigonometric functions and rational functions in x. We can deal with either rational functions in x or with trigonometric functions in x, but not both at the same time. So the first step is to use a partial fraction expansion, which will hopefully separate out rational functions in x from trigonometric functions in x. Since the denominator of the integrand factors as x squared plus 1 times cos squared x, we want to rewrite this fraction as something on x squared plus 1 plus something on cos squared x. If we can do this, then multiplying a by cos squared x and b by x squared plus 1 to make the denominator on the right hand side the same as the denominator on the left hand side. If we do this and it all works, then we need this to be equal to this. Because the left hand side has got a cos squared x, we want cos squared to appear on the right hand side as well. So the trick is that sine squared x plus cos squared x equals to 1. Therefore we can replace sine squared x with 1 minus cos x. Now when we compare the left hand side with the right hand side, we see that to get the cos squared x terms to match up, we need a to be -1, and to get the x squared plus 1 terms to match up, we need b to be equal to 1. We can check that indeed 1 on cos squared x minus 1 on x squared plus 1 is equal to our integrand here. This has achieved our aim of having one term involving only trigonometric functions and another term involving only a rational function of x. The problem thus reduces to evaluating these two integrals here. Option 1 is to just recognise that if we differentiate tan x, we get 1 on cos squared x, or sec squared x. And so therefore the indefinite integral of this is just tan of x. And similarly, 1 on 1 plus x squared can be recognised as the derivative of arctan x. Therefore, the indefinite integral of this one is just arctan x. For the first integral, there's a general theory that says if you have a rational function of sine squared and cos squared, then it can be reduced to a rational function via the substitution u equals tan x. And we'll take this approach just to demonstrate how it works. For this particular one, it's going to be quite trivial, but it works in the general case too. If we had a rational function of sine x and cos x without the squared there, then the correct substitution to reduce to a rational function would be u equals tan of x on 2, and we'll explain why this works later in the video. For a rational function here, it can be computed the standard way by using a partial fraction decomposition. That would mean, though, introducing complex numbers, and the answer you get would involve a complex logarithm. To simplify this, then the trick is to use x is equal to tan u. In some sense, the opposite of this. This is u equals tan x, this is x equals to tan u. When we have a rational function involving only sine squared x and cos squared x, then the substitution we use is u equals tan of x. To make this substitution, we have to know what dx is, so we have to differentiate tan of x. If you can't remember the formula for that, then express tan of x as sine of x divided by cos of x. then apply the division rule. If we differentiate this, we have got with u as the numerator and v as the denominator, v du minus u dv all on v squared. That's the division rule for differentiation. So to apply that rule, we start off with the denominator, cos of x, multiplied by the derivative of the numerator. Derivative of sine is cos, so I've got a cos squared x term here, minus, now we do the opposite. We write the numerator, sine of x, then we multiply it by the derivative of the denominator. Derivative of cos is negative sine, so our sign changes to plus, and we've got sine squared x. The denominator down here is just the denominator squared of the original expression, so I've got cos squared x here. Since cos squared x plus sine squared x equals to 1, we see that the derivative of tan of x is 1 on cos squared x, or sec squared x. This is the simplest case where we recognise that dx divided by cos squared x, dx divided by cos squared x is just du. So in this simple case here, we end up that this integral here is just u plus a constant, in other words tan x plus a constant. In general, what we would need to do with this substitution is we need to work out how to express sine squared and cos squared in terms of u. Remember, this substitution is only when we've got terms involving sine squared and cos squared and integer powers of those. To work that out, we just draw this simple right angle triangle here. X is the angle. If tan of x equals to u, then that means that the triangle, if this base length here is 1, then this side length here is just u. That means the hypotenuse is going to be the square root of 1 plus u squared by Pythagoras' theorem. And we can now read off sine of x is equal to u divided by the square root of 1 plus u squared, and cos of x is 1 divided by the square root of 1 plus u squared. Since we don't want to be integrating square roots, that's why this substitution is when we've got terms involving powers of sine squared x and cos squared x, because if we sine these expressions, we get u squared on 1 plus u squared and 1 on 1 plus u squared, thereby converting a rational function involving sine squared x and cos squared x into a rational function of just u. Similarly, we can work out what dx is. We know from here that du equals dx on cos squared x, but we need to write this in terms of u. And we just saw that cos squared x can be written as 1 on 1 plus u squared. Therefore, in the general case over here, we replace sine squared x with u squared on 1 plus u squared. We replace cos squared x with 1 on 1 plus u squared, and we replace dx with 1 on 1 plus u squared du. And if we did this directly, we'd find that the reciprocal of this times this is equal to 1, and we're left with the integral of du as we had here. A rational function can always be integrated, and the integral will be a rational function plus possibly some terms involving logarithms. Where do logarithms come from? Well, the derivative of log of x is 1 on x. So, and the reason why there's this exception, so to speak, is we know that the derivative of x to the n is nx to the n minus 1. And so normally, if we want to integrate x to the n, we get x to the n plus 1 on n plus 1. But that fails for 1 on x. Because the next power up to 1 on x, which is x to the negative 1 plus 1 is x to the 0, which is a constant. And when you differentiate a constant, you get 0. You don't get back 1 on x. So that's why rational functions, when integrated, become rational functions plus one or more terms involving logarithms. To integrate this, the traditional way, you would use a partial fraction expansion to simplify it. Because we have x squared plus 1 has got no real roots, we've got imaginary roots, we end up with an expression involving complex logarithms. And you can actually show that that is equivalent to arctan x in this particular case here. Another way of arriving at arctan x, besides just having differentiated this and know that its derivative is this, is via the substitution x equals to tan u. On the last page, remember we had u equals to tan x. So in some ways the substitution here is u equals arctan x, but we write it as x equals to tan u. If we differentiate this, then we know from before we get 1 on cos squared u, therefore dx is 1 on cos squared u du. So when we substitute x equals to tan u in here, we get 1 on 1 plus tan squared u times dx gets replaced with 1 on cos squared u du. Tan squared u is sine squared u on cos squared u. When we multiply everything by cos squared, we therefore get 1 on cos squared u plus sine squared u. That's equal to 1. Therefore, I get the integral of du, which is u plus a constant, which is arctan x plus a constant. We can now solve today's integral, which was 30 times this integral here. By applying partial fractions, we know this splits up into two terms. The integral of the first term was tan of x. The integral of the second term was arctan of x. There was a minus sign between the two terms. So we get that this is the definite integral when evaluated between x equals to 0 and x equals to pi on 4. Therefore, we get 30 times, evaluate this at pi on 4, and subtract away whatever we get when we evaluate this at x equals to 0. Tan of pi on 4 is the same as tan of 45 degrees, which is just 1. Arctan pi on 4 needs to be done numerically. We get approximately 0.6658. Tan of 0 is 0 and arctan of 0 is 0. So we end up with approximately 10.02. The general substitution for a rational function involving sine and cos is u equals tan x on 2, and we will explain where this comes from. The key idea is to look for a rational parametrization of the circle in one variable. And the way that's done, and this has been known since before Euclid, I believe, the way this is done is that you can pick a point t units up on the y-axis. The other point will be fixed at -1, 0. We draw a straight line between these 2 points, and we look to see where it intersects the circle. So as we vary our point t up and down, we trace out an arc on this circle. And in fact, by sending t to be very large or down to being very small, we can actually reach every point on the circle except this -1, 0 point here. We need to determine the coordinates of this point of intersection. Given any value of t, we want to know what this point here is. To do that, we have a pair of simultaneous equations. We've got the circle defined by x squared plus y squared equals to 1, and we've got our line, which is easy to see is y equals tx plus t. Indeed, when x is -1, this gives y equals to 0, which is correct, and when x equals to 0, it gives us y equals t, which is also correct. If we substitute the second equation into the first, we will get a quadratic equation in x, but we don't want to use the quadratic formula because we already know one solution is x equals to -1, and we want to find the other solution here. We still do the substitution to get our quadratic equation here, but rather than solve this quadratic equation, we know that it factors in this form here because it's a quadratic equation, and we know that one of the factors is -1, and we know either by expanding this or having memorized it that this term here will be the product of the two roots. So we know that lambda1 lambda2 equals t squared minus 1 on 1 plus t squared, and we know lambda1 is -1. That's where the line intersects the circle back here at the point -1, 0. So that gives us that the second point of intersection, lambda2, is given by 1 minus t squared on 1 plus t squared, just -1 times this guy here. Once we found x, we simply have to substitute this solution back to get y, and so we see that the point of intersection has got x coordinate 1 minus t squared on 1 plus t squared, and y coordinate 2t on 1 plus t squared. We can check that this is correct by substituting the two answers we got back into the first equation. We used the second equation to derive y, so we check with the first equation, x squared plus y squared, substitute x in, substitute y in, and evaluate it. We've got the expression at the top here is going to be 1 minus 2t squared plus 4t to the fourth plus 4t squared. The 4t squared here changes the negative 2t squared into a positive 2t squared. That then makes this equal to 1 plus t squared all squared. So it cancels with the denominator. We get 1 as required. This is the picture we have so far. We've got our unit circle, our fixed point here. This point allows us to vary t to get different points on the circle. As we vary t, the corresponding point on the circle will have coordinates 1 minus t squared on 1 plus t squared, comma 2t on 1 plus t squared. If we call this angle here theta, if we draw a line from the origin to this point here, call that angle theta, we have got that the hypotenuse has length 1, that this side here is sine theta and this side here is cos theta. So this point here is equivalent to the point cos theta sine theta, where theta is defined by the angle between the horizontal line here and the line from the origin to the point of intersection here. This means that an integral involving sine theta and cos theta, which can be thought of as integrating some function on the circle here, can be changed into integrating a function where cos theta is replaced by this, sine theta is replaced by this. So now we're integrating a function in t, and we see that it will be a rational function in t if the original function was rational in sine theta and cos theta. Just to help illustrate what's happening, assume we have an integral involving sine theta and cos theta, and we integrate with respect to theta. In effect, we're integrating over this circle here, because as we change theta, sine theta and cos theta are going to trace out a point on this circle here. Although theta is just a real number, and we normally think of this as just a function of a real number, what we're really doing here is we're thinking of this function factored in the following way. First we go from theta to this point cos theta sine theta on the circle, and then we go from this point on the circle into the function here. And so in this way we're treating this function to be integrated as a function on the circle. So by treating this as a function on the circle, we can then simply replace one parametrization of the circle by another parametrization of the circle. Here we parametrize the circle in terms of theta, and over here we parametrize the circle in terms of t. So if in our original integral we went from, say, this point on the circle all the way up to this point on the circle, then we want to do the same over here. We want to vary t, so we go from this point on the circle up to this point on the circle. Substituting 1 minus t squared on 1 plus t squared for cos theta, and similarly 2t on 1 plus t squared for sine theta, is simply treating the integrand as a function not on the real line, but on the circle. And it's replacing this parametrization with this parametrization of the circle. Rigorously, we can think of this function as the function f on the circle. Given a point xy on the circle, this function's just 1 on x squared. The reason is because when we parametrize the circle by cos theta, sine theta, the x-coordinate is cos theta and the y-coordinate is sine theta. So 1 on cos squared theta, cos is the x-coordinate, that's 1 on x squared. So our original integral is integrating a function on the circle parametrized by cos theta sine theta, and then we want to change it into the integral of the same function on the same circle but parametrized by t. And the parametrization in t now gives us x and y coordinates of this and this. we will need to change the rate of change here. So we need to work out how d theta and dt are related, and that function goes in here. So in our original integral, the first question is, what is d theta going to be replaced by? Because as I vary t, the rate of change along my arc length might vary. It won't necessarily be the same as d theta. Also, if I'm integrating from 0 to pi on 4, I need to work out what the corresponding limits in t are. T goes from what to what in order to trace out the same region of the circle. The trick to answering these questions is to notice in this diagram here, which we used to work out our parametrisation to begin with, that we actually have an isosceles triangle. Because this is a unit circle, both this length and this length are 1, making this an isosceles triangle. If the angle here is theta, then the angle here is 180 degrees minus theta. And because the angles of a triangle sum to 180 degrees, that means that this angle plus this angle has to equal theta. And because it's an isosceles triangle, this angle and this angle are the same, therefore this angle is theta on 2. And from this diagram here we can derive double angle formulae as well, by the way. It now follows, because we have a right angle down here, that t is just tan of theta on 2. This length here is 1, this length here is t, so tan theta on 2 is t divided by 1. T equals tan theta on 2. We can now summarise the reparametrisation of our integral. Here's our basic picture to remind us of what we're doing. Rather than parametrise the circle using cos theta sine theta, we're going to parametrise the circle using 1 minus t squared on 1 plus t squared, comma 2t on 1 plus t squared, where t is the point where this line passes through. The relationship between the two parametrisations is given by t equals tan theta on 2. We can see from this diagram here, and we already know, that cos theta is the same thing as 1 minus t squared on 1 plus t squared, and sine theta is the same thing as 2t on 1 plus t squared. Of course, we also have tan theta, which is sine theta divided by cos theta, which would be 2t divided by 1 minus t squared. And we're going to use that shortly. Now we know the relationship between theta and t, we can work out what d theta is. We simply have to differentiate this expression here. So we get dt on d theta equals the derivative of tan is sec squared. So the derivative of tan theta on 2 is a half sec squared theta on 2. We need to write the sec squared theta on 2 in terms of t. So we draw this little diagram here. If this angle is theta on 2, if t equals tan theta on 2, then that means that the ratio of this side to this side is t. So we may as well make this length t, this length 1. Pythagoras' theorem says that the hypotenuse is the square root of 1 plus t squared. And so therefore cos of theta on 2 is going to be 1 on the square root of 1 plus t squared. So sec theta on 2 will be the square root of 1 plus t squared. And sec squared theta on 2 will be just 1 plus t squared. This is the substitution to use if we want to integrate a rational function in sine theta and cos theta. It will convert the integral into a rational function in t. While we will apply it to this function, this is going to be a tedious integral to evaluate this way. When we've got sine squared and cos squared, then it's much faster to make the substitution t equals tan theta rather than t equals tan theta on 2. Nevertheless, we are able to get the same answer both ways. From our original integral, we make the substitution t equals tan theta on 2. That means that we replace cos theta with 1 minus t squared on 1 plus t squared from this diagram here. Sec squared theta is therefore going to be 1 plus t squared all squared divided by 1 minus t squared all squared. The d theta term, we know that d theta equals dt divided by a half 1 plus t squared, which we have over here. So after substituting t equals tan theta on 2 into this, we get this expression here, which simplifies to this one here. The reason, of course, that the limit of integration is now tan of pi on 8 is because we have made the substitution t equals tan theta on 2. When theta equals 0, tan of 0 divided by 2, tan 0 is just 0, so that limit stays the same. When theta is pi on 4, we've got tan pi on 4 divided by 2, which is tan pi on 8. At this point, we need to perform a partial fraction decomposition, and we do this on the next page. Continuing on, this is where we left off on the previous page. 1 minus t squared is equal to 1 minus t in brackets times 1 plus t in brackets. Performing a partial fraction decomposition, where we need to note that because the denominator now involves powers up to t squared, then in the numerator we have to allow powers up to t, but in this particular case we don't need them. Rather than perform the partial fraction decomposition, I just leave it up to you to check that this is indeed the same as this. And so to perform this integration, we need to integrate this term and this term here. We know that if we want to integrate 1 on t squared, then we essentially get 1 on t up to sine. In other words, if I differentiate 1 minus t to the power of negative 1, then I'm going to get negative 1 times 1 minus t to the power of negative 2. And in this case, because I've got negative t, that will change the sign out the front. So I get 1 minus t to the power of negative 2, which is the first term here. And similarly, to integrate this term here, then I guess it's of this form here. I differentiate this, and I find that I'm correct up to sine. So this tells us that the integral of this expression here is given by evaluating 1 on 1 minus t, for this corresponding to this term here, minus 1 on 1 plus t, corresponding to this term here, from 0 to tan pi on 8. If we differentiate this, we get this, and if we differentiate this, we get negative of this. This simplifies to this, and then we first of all evaluate it at tan pi on 8, and then we evaluate it at 0. However, tan pi on 8 is not such a nice number, and there's a trick. We can recognize this corresponds to a double angle formula. From the previous page, we know that tan of 2 theta equals 2 tan theta on 1 minus tan squared theta. Indeed, if t equals tan theta on 2, then we saw on the previous page that tan theta was 2t on 1 minus t squared, and that leads directly to this. So this, when t equals to 0, is just 0, so evaluating this means it's 2 tan pi on 8 divided by 1 minus tan pi on 8 squared. And we recognize that as the right-hand side here, so this is just the same as tan of pi on 4, which we know equals 1. And this is indeed the same answer that we got before. If the integrand only involves even powers of cos theta and sine theta, then as we said at the start, it's a lot simpler to use the substitution u equals tan theta. In the general case, that means we then draw this corresponding triangle here, theta's here, u and 1 are here, so that tan theta is indeed equal to u. By Pythagoras' theorem, the hypotenuse is the square root of 1 plus u squared, so we read off from this triangle that sine theta should be replaced by u on the square root of 1 plus u squared. Sine theta is the ratio of this length to this length, and cos theta, being the ratio of this length to this length, gets replaced by 1 on the square root of 1 plus u squared. So for example, to perform this integration here, without immediately just recognizing that this term here becomes du, then what we do is we replace the limit of integration by tan of the value. So we go from 0 to tan of pi on 4. We replace sec squared theta by using this formula here to get 1 plus u squared. And then we need to work out what to replace d theta by. So again, we differentiate this. We get du equals sec squared theta d theta. That means d theta equals cos squared theta du. And then from this diagram here, we see that cos squared theta is 1 on 1 plus u squared du. So d theta gets replaced by 1 on 1 plus u squared du. In this particularly simple case, these two terms cancel, so we get the integral from 0 to 1 du, which is equal to 1. Again, the same answer as before. There's a very practically important reason for understanding where these change of parameters come from. And that's because if we're not careful, we'll make mistakes with limits of integration. For example, the first trap is if we're asked to evaluate an integral involving sine and cos between 0 to 4 pi. We make the substitution u equals tan pi on 2. And if we naively just change the limits of integration to tan of theta on 2, well, 4 pi becomes tan of 4 pi on 2, which is 0, and tan of 0 becomes 0, so we just get 0 for the answer, which is clearly incorrect. What's happened is that the integral we care about is going around the circle twice. When we change parametrisation, it's impossible to go around the circle twice. We can go around the circle once by letting t go from negative infinity to infinity. There's still a trap if this were the integral from 0 to 2 pi. Tan of 2 pi on 2 is 0, so we'd have a similar problem. We have to recognise how the parametrisation works. In particular, when we parametrise in this way here, then as u goes from negative infinity all the way up to infinity, theta goes from negative pi round the circle to pi. And so we can have an integral from negative pi to pi correspond to a matching integral in u from negative infinity to infinity. To evaluate this integral then, we need to recognise this as being 2 times the integral from negative pi to pi of this expression here, and then we can replace that with 2 times the integral as u goes from negative infinity to infinity. With the parametrisation u equals tan theta, which we can use for functions in sine squared and cos squared, the problem is that we haven't yet discussed how the parametrisation works. And in fact, we're going to find out that we can only parametrise the right-hand side of the circle. So if we try to integrate from 0 to pi, we're going to run into problems, for example. Making the substitution u equals tan theta is illustrated in this diagram here. The angle here is theta. The corresponding point up here, which we worked out from this triangle here, has got coordinates given by this and this. But this picture here doesn't show us explicitly what u is equal to. Well, in this diagram here, we have a base length of 1. So what we can do is we can actually draw a line here that is at the x equals to 1 coordinate, and the u parameter is given by extending this line here all the way out until it meets the green line here. And now we see that as we vary u from negative infinity to infinity, we trace out the right-hand side of the circle here. Mathematically, we can see this is what's happening because the x-coordinate here is 1 on the square root of 1 plus u squared, and this is always positive. So at best, we can get only the right-hand side of the circle. As mentioned, if we naively try to perform this substitution for an integral from 0 to pi, we run into trouble because our parametrisation actually doesn't extend into the left-hand side of the circle. If we were to naively substitute u equals tan theta into this integral equation here, we get a limits of integration from 0 to tan of pi, which is again an integral from 0 to 0, so we get the wrong answer. How do we solve this? Well, in general, we use symmetry. For example, we know that sine squared theta is going to look the same in the first quadrant as it does in the second quadrant. So therefore the integral from 0 to pi of sine squared theta d theta is just 2 times the integral from 0 to pi on 2 of sine squared theta d theta. And in this region here, we can apply the appropriate parametrization. Now, as a note, if we really did want to integrate sine squared theta d theta, while this method would work, it's very tedious. And instead, what you would do is you'd use a double angle formula to rewrite sine squared theta as a half 1 minus cos 2 theta. The key point though is don't naively make substitutions, understand where they come from and understand their limitations. In this case, by making substitutions u equals tan theta or u equals tan theta on 2, we're reparametrizing the circle and we need to be careful about what our reparametrization can do.